challenge round number 8. 8. Yes. Okay. 8. 好。
What was the title of the problem?
Equipotential line. Let's do this. Okay. This one. So reject. Okay. Challenge problem 15, boycott effect. We have STAGE. Okay, so the problem number 15, boycott effect. Let's have it.
还是快到有点。我觉得我们这个报也没有什么问题。我觉得我们这个报也不错，不应该6分。他的美国那个比赛太对，有些觉得很好，有些很麻烦。而且像马尔他很在意对theory 要不要太多，不是有点新闻。是我。啊，有啊，OK，没关系。 对，就让
Please be careful. Please.
If particles are expanded in a liquid that has low density particles, then the particles will settle to the system of the liquid. The rate of settling can be affected by filters in this container that holds the liquid, and we need to explain the phenomenon and investigate the effect of the phenomenon. The Boycott effect generates an action when the implied upper surface image is introduced into a suspension of heavy particles. The particles settle gravity and they are creating a layer of particle fluid surrounding the surface. The created fluid in the layer is bound and so sampling in the surface wall. The tangent tangent gas of the fluid around the wall requires the fluid
We need you to speak louder.
so I will try. The tangential gradient in parts of the fluid around the wall requires that the fluid is drawn from the suspension into the particle fluid layer. The resulting drag balancing degradation of most of the particle dynamics was expected to be different. The resistance is bounded layer with the stiffness as well as the distance around the wall as resisting. So we have more cards. So this is A represents so the separate line between the fluid and the particles, and then we have B the portion with only C particles, C where there is still with fluid, and D where the particles the particles are more dense. I will introduce the theory from February 1995, Nakamura and Brodak and 87. It aims to predict the sedimentation rate for a modest road suspension in a parallel trajectory. And then we have the T, the T equals minus B01 plus H for B times sin A. So that would mean that H density T is minus H of T is minus B times 1 sin A plus B minus T plus 0 sin A over B. That times H is 0 plus B times 1 sin A, where H is the height of the suspension at the time, B0 is the suspension because it's the container of the cell dimension, and B is the width of the container, and A is the angle of the container. So that was close, and to express the sustained velocity of a single particle in an infinite rate problem. So we have the sustained velocity of a single particle, V0, equals the square times lambda minus 1 times G over 8 dk, where G is the particle diameter, lambda is the ratio of the particle density with the fluid density, G is the rotation acceleration, and here is the fluid segment the force of viscosity on a small field moving through a viscous fluid is given by F equals 6 pi times V. And this is the initial law of Stokes, which was modified by the first formula. We have the function of force, Stokes drag acting in the separation between the fluid and the one part. In our calculations for T, we see that H3 for each line that has separation line between the clean liquid and the one which reaches 1 mole. For sample figures of diameter which equals 0.22 millimeters set to second derivative of table, we have that from 250 for 1030 kilograms of meter cube, and the sample would be 1600 kilograms. Of course, we studied it and the sample equals to obtain almost complete picture, and then we did the measurements of the line, and we did the measurements for 0 degrees, 50 degrees, and plus. If we introduce H0 equals 10.75 meters, so that H0 of theta is the building angle will be H0 times cos theta minus 3 times 4. This is the initial rate of the mixture, so that we can increase the power as it is stated. B is the length of the side of the rate of the toilet, where B is 7 centimeters, and then we introduce the calculations. We will have that 0 is 0 plus 0.268 because for this liquid we have F equals 65 millimeters per minute. The experiment realized at 0 degrees had H2 equals H0 minus H0 times T. This is because the particles are very small and we have the constant force, and there is almost no friction between the particles. Then we have the constant velocity is 0, and therefore the particles will be the constant speed. For the results, here we have the correlation between the results of the experiment and the clinical theory. We see that they're very similar, and we did experiment in 6 for 0 degrees, 50 degrees, and 30 degrees. We see that for the vertical one, we have a linear function because the speed is the same over time. And for the other ones, we have a set growth. So we have a coordinate. So recently we in terms of the density of both the fluid and the particles, also the viscosity of the fluid. The theoretical models are not taking into consideration the friction between the particles, and therefore the results are not exactly as we fluid. But because the particles are very small and there are not a lot of particles in the fluid, because it was a large container, then these forces are very small, and as it can be seen because the results are almost the same in the experiment as in T. We did the results at the temperature of approximately 25 degrees Celsius, so that the rotation will be so the temperature is considered and we can observe that the two layers that are formed are exactly the model, and the second one is formed very fast. So that is why we need to have into consideration the height of the first layer, the height of the first layer. And we can observe that the more similar the faster the particle settle, the second is practically demonstrated to be influenced as interior by the tilting angle and the particles and fluid interface. The viscosity, even when conducting the experiment in the home environment, as I said, 35 degrees, we can sensibly approach the viscosity. So
very much. Thank you for your presentation. So first, I just have to clarify. Can you go to page 12? What did you observe to quantify the settling rate? What exactly did you observe?
I observed, so if we go to the first, no, the second slide.
Did you observe like can you go to the diagram? Did you observe like the interface between this system layer and the hardcopy layer?
Yes.
So you mentioned that boycott affect enhanced segmentation, and can you be more specific? Which part of it? How does it enhance segmentation?
How does it affect segmentation?
Enhance segmentation. How does it enhance make segmentation faster?
Okay, so it makes segmentation faster because at first the initial height is lower at first, and then we have that a lot of these tends to remain on the side of the parallel thread, and then we have fewer particles that need to set.
Also, is it because there's convection? Is convection main part of the confused? Well, if we go to page 13, what do you mean by two layers? 13, it's like 13.
Two layers, sorry.
Okay, what do you mean by two layers?
The two layers the one that was very high in the density of particles, the one from. So if you get the first image. So these are the two layers.
These two layers, C and D.
Oh yes.
Okay, and
B and D.
B and D. Okay. So that's all my question. Okay, thank you very much. It's time for questions now.
We channel with the cable. We don't get around it.
Okay, so for this one explanation, clarify the short version that convection is the main effective causes of the sedimentation to be enhanced, but we will elaborate on that later in the discussion. And also, they explain the Stokes equation by explaining that gravitational force downwards has to balance the drag force upwards. So we get a relatively clear explanation of the Stokes drag, but the explanation for how Boycott effect enhances sedimentation were not very clear, and they did not discuss what exactly the sedimentation rate means. For step 2, they cited the Iypt theory, but there were no decided Iypt theory, but there was no derivation or for the limitation of Iypt theory. They also explain, they also derived the Stokes law for us. And they do have quite a lot of derivations for Stokes law, but they only read through the equation, did not express the physical ideas, and we didn't see the limitations for the Iypt theory and what it actually means. Okay, and for step 3 is the experiments, and for the parameters, they changed the tilting angle, and they used markers to help measure the initial height. So they have replicable experiments, but the experiments we couldn't really tell the different layers, like the particle layer, the suspension layer, and the really compact sediment layer that was mentioned in the diagram, and they did not define the interface. We did not see the clear interface between the suspension and the clear fluid layer. And with this the reporter could actually investigate more parameters. Yes. And for the data analysis, we noticed that all experimental lines are a little higher than theoretical, and the report stated that the deviations should be caused by friction between the different particles. So we did compare the theory to the experiments, but we didn't exactly see enhancement. So for the experimental data, the slopes were pretty much the same, and for the tilting, for varying the tilting angle, the theoretical settling rate didn't change much at all. So I think this part weren't enough developed to verify that tilting actually increases the sedimentation rate. Okay. So we would like to discuss what the Iypt theory actually means, what are its limitations, and how do we use it, and what relevant parameters we should be observing to prove that Iypt theory is applicable for this situation. And for experiments, we'd like to discuss the formation of the particle layer and how it relates to convection and how that enhances sedimentation, and how different parameters such as changing the viscosity, changing particle size, and changing the density doesn't just affect the Stokes velocity, it also affects how the Boycott effect enhances the sedimentation if you just scale the Stokes velocity off. And finally, we'd like to discuss how the tilt angle is related to the enhancement of the sedimentation rate. So I would like to invite the reporter up for some discussion.
Okay, please, let's start the discussion. Please come.
So you mentioned that Boycott effect enhances sedimentation rate.
May I suggest that we connect the reporter's presentation?
So you mentioned that convection enhances sedimentation. Yes, I also read the reference you cited. I think there's like a clear definition, a clear explanation for how convection enhances sedimentation. So let's say this is the original, this is a clear container, and your particles are mixed in with the solution. So if there were no convection, all the particles would just fall vertically down, and you will get a thick layer of near the outward-facing wall. So what convection actually does is that it takes the water from this layer and piles it on top. So instead of getting this shape, you get a very thin layer near the outward-facing wall, and the water actually accumulates here. So the settling rate is same for is the same if you just measure how the weight of the sedimentation, the weight of the sedimentation that accumulates during a specific amount of time. But if you look at the top of the suspension layer, the interface between the suspension mentioned in the clear particle, and the clear particle layer is actually, this is actually what is enhanced because convection piles up the water here. So I think that's a third explanation for how convection actually helps in enhancing the sedimentation rate. Okay, and have you, do you know about any limitations of the PNK rule, of the PNK theory? What are the limitations?
So the limitations are the first idea would be that they don't take into consideration the friction between the particles, the interaction between the particles in general. And
Wow. Okay, so is that the only limitation or?
no, it's not the only limitation. The limitation is that it doesn't take into consideration the temperature, either viscosity will be taken into consideration by viscosity.
Also, so it's like saying that the V0 is the same for all the particles, or what are the limitations?
The particles are not of same dimensions, so this is for particles of same dimensions.
So the limitation that the particles have to at the same size. So I believe another very crucial limitation of the PNK theory is that because, as we just explained, convection takes the water from here and piles it on top. So PNK is a purely geometrical observation. So what it says is that, let's say the suspension layer is initially this tall, so the effective settling area is this. And let's assume that all particles have the same velocity, so the amount of particles that will settle in the amount of time will be equal to V naught times this effective area. And it just assumes that the particle fluid that has to go up, they all accumulate on the top here. So it doesn't consider the limitations to how fast convection can take fluid from here to here. So this is equal to the change in the height times this area here. Let's just call it area of accumulation. So by writing this equation and then just plugging in the value for the effective area and the area of accumulation, you can derive this equation here. So this is purely geometrical. It doesn't take into account how convection piles the water from near the occupied wall to here. Okay. So
Yes, actually, if this water is clean and there are no particles, the differences will not be so high as you can see in the experimental theory.
can you show me?
They're almost the same.
I mean, because you know the slope is just like vertical settling. So even if it is like because the slope is so similar, I don't think you can just justify that the sedimentation is enhanced because the slope is so similar. So because your theoretical line is very much, just saying that the lines match, I don't think that's enough to say PNK is accurate for the prediction. But I want to move on to another discussion. So did you observe this? You said that you observed these two layers here. They're very clear. This small particle-free layer. Can you show me a photo of that?
So the line isn't really clear in the video because the line.
Can you show me where the line is, the way you see it?
Do you want me to bring it?
Okay, so is it here or I don't see a very clear particle-free layer here.
Yeah, it's very clear when it's not in the video, and it's extremely clear.
So does it remain thin and like relatively independent of time?
Yeah.
Okay, so thank you. Okay. So how do you think? So by writing this equation, we get that the settling rate is proportional to V naught. And you can change V naught like in your report by changing the Snow's settling velocity. So you can change, for example, the particle size. you can change the particle size, and you can change the viscosity. So do you think by changing these different parameters, let's say the initial settling rate is like this, and if you change these parameters and you get a V prime that is equal to 2 times V naught, will the sedimentation rate be like just this, but scaled by 1/2? Do you think the settling rate will be similar in shape? You just scale it with V naught.
Well, it will be similar in shape because I actually did the experiment with more particles,
Different particles, yes.
with larger particles, and it was also very similar.
The shape.
Yeah.
Okay, so you change the size. How large was the particle?
The particle was about 3 times larger than this one.
I mean, like, what's the particle size of this one?
This one is, I think, 0.20 millimeters diameter.
But that's very large. Okay. Can you go to page 13? Oh. There's the page with the setting velocity, the setting curve. Okay, thank you. So just as I mentioned, the slope of these 3 experimental lines are very similar. And can you tell me if so I don't think there's actually enhancement of sedimentation here, and because what the indicator theory says is your particle has to be very, very small. It was initially observed for red blood cells, and red blood cells are on a scale of microns. The particle, the radius has to be very, very small. So if it is just a very large ball, it can just settle vertically, and you can calculate that with just the slow settling speed. So I think because you have such a large particle, it actually doesn't satisfy the conditions for the Iypt theory, or it doesn't satisfy the condition for the sedimentation to be enhanced. So you get these slopes that are very similar. Yeah. Okay. And then,
I have a question. Why does the diameter, I mean, it's not extremely large. Why would it be such a large difference?
such a large difference.
Because between V equals 0.32 millimeter and E equals about 100 millimeters, but the distance wasn't that large. So why?
Well, because I think for your experiment, because it was like on scale of millimeters already, so these were already like descending just like described by Stokes settling. So it isn't influenced by Boycott effect at all. So you didn't observe the difference. I think that's the main cause.
There was a difference.
There was a difference.
They are not quite.
Do you have a graph of a different particle size?
No, I have one, but
Okay, thank you. What's the vessel width and what's the vessel width and the height of the fluid for this experiment?
okay, so
The vessel width is 20.
about 31 centimeters.
And what's the base? The base is
The base is 7 centimeters.
7 centimeters. Okay, so it's like this.
Yeah,
Okay.
and it's very large. The particles are very small.
Okay, so can you go to page 11 again? So I think the reason why the theoretical line the reason why the theoretical lines are like so similar is because just as we discussed, the sedimentation rate is enhanced by the factor of you just move A effective to here, by the factor of move this here. Yeah.
I'm sorry.
Okay, thank you.
Time's up. Thank you very much, but you still have 1 minute to sum up the discussion.
Okay, so in this discussion, we explored how convection actually helps enhancing the sedimentation rate, and then we also clarified that in the reporter's experiment, the clear fluid thickness has to be remaining thin. And when we look at the experimental graphs, we can see that the experimental slopes were too similar, so we couldn't actually say that tilting a container enhances the sedimentation effect. And another reason for this is that the particle is too large, so that doesn't match the Iypt requirements. Okay.
questions from the reviewer? You reported the opponent was very intensive discussion. To the reporter, did you assume the particle is spherical?
Yes, because they were very small.
I see very practice by using a microscope.
No.
I see, okay. To the reporter, how did you mix the mixture?
I mixed them. Actually the parameter was a bottle and I just mixed it to be
I see. And to the opponent, do you believe that this is a valid way of, accurate way of mixing the mixture?
I think we have used like good larger machine to make sure that
Yeah, I see. To the reporter, what liquid did you use in your experiments?
I used fluid detergent.
Do you know roughly how viscous the fluid detergent is?
Yeah, BF was 55 millimeters per seconds.
I see. To the reporter, how did you track the interface? Is it tracked by eye? Did you track the movement of the particles by eye?
Yes.
I see. To the opponent, do you believe that this is valid?
I think this depends on the experiment. If there is a clear interface, a sharp interface, that you could track it by the eye.
I see. To the opponent, you mentioned that the PNK theory is not applicable for larger particles, right? Could you briefly explain why?
So for large particles, its radius to the vessel is too close to the radius of the vessel. So you would just be getting like slow settling. So you cannot just pack a bunch of particles in here and then would have mass convection. You don't get mass convection.
Okay. To the reporter, what is the radius of the particle? What is the particle radius?
The diameter was 0.2 millimeters, so the radius was 0.2.
And roughly how big is the container?
The container was a lot bigger than the particles. It was 7 centimeters times 21.
And to the opponent, now do you believe that it is valid to use the PNK theory for such particles?
No, because PNK theory gets more accurate the smaller particles you use.
I see. Okay. Okay. Thank you. To the opponent, do you feel that the volume of fluid within the container is very significant? Do you believe that the volume of fluid within the container is a relevant parameter to the problem?
Volume of fluid? No.
I see. To the reporter, do you believe that this is a valid parameter?
Yes, I think this is a part.
I see. To the reporter, are your containers rectangular?
Yes.
Okay. What particle concentration did you use in your experiment?
Excuse me?
What particle concentration did you use in your experiment? Like the volume fraction of particles?
And the volume section of particles, so it was 7 centimeters times 3 centimeters, so 30.
Okay, thank you. What is the viscosity of the Okay.
Sorry, time's up. Thank you very much. Now preparation of the review.
report. For respect to the report, I think that the reporter has demonstrated a good predictive power of the analytic model of the PNK theory, and this gives us some physical impact with the enhancement of settling velocity. Next, the reporter has investigated the effect of tilt angle which is required by the problem statement. And lastly, it identified convection as the driving effect of the phenomenon. However, I believe that there are many areas of improvement for the report. Firstly, there was an unsatisfactory qualitative explanation for a number of factors in the report, like the development of the convection currents. And I believe that this is very important, as the convection currents directly govern the fluid flow. And I believe that a possible explanation for this is due to the pressure gradient formed between the suspension layer and the clear fluid layer, resulting in buoyant force affecting the clear fluid of the container. And they also note the significance of an enhancement in base area, and with a larger base area, there will be a larger amount of fluid settling per unit time, resulting in more fluid being produced. Next, there was no discussion into increased settling velocity due to an increased effective base area, and I believe this is very important, as the increasing effective base area means that more clear fluid is being produced. Next, there was no discussion about the sediment layer formed at the bottom of the container, and I believe this is very important, as particles settle. Clear fluid is being, as particles settle, they form a sediment layer with high particle concentration, resulting in a lower settling distance affecting settling time. Next, the reporter failed to account for the interaction between particles, which will mean that the settling velocity decreases. Next, there was a poor experimental control, as stirring the fluid imparts initial velocity which will affect the settling time, and I believe that the reporter could have used a more viscous fluid like construct to reduce the effect of this, and the interface was also checked by eye, which I believe is not very accurate and requires these computational methods to check the interface. Lastly, there was a poor experimental scope as the reporter failed to investigate the effects of particle concentration, base area, and fluid volume. So moving on to the opponent, they rightly pointed out the lack of significance of the convection current, and pointed out the lack of discussion on the physical significance of the PNK theory, and lastly discussed the lack of investigation into many relevant parameters. But I think that there are quite a few missing points, like how the interface is tracked by eye, and the origin of convection current not being discussed, and lastly the effect of the volume of fluid in on the settling time. And the reporter has brought up a trivial point for the viscosity of the fluid, and I believe this is not very physically significant to the problem, and the viscosity of the fluid would reduce the terminal velocity, which is quite intuitive. So moving on to analysis of the discussion, firstly, the reporter and opponent have discussed the significance of convection, and I will partially agree with the opponent that convection drives the water out of the container affecting settling time, but the sedimentation rate also changes as the effective base area of settling changes, resulting in more clear fluid being formed. Next, the opponent has discussed the limitations of the PNK theory, and the opponent believes that the PNK theory assumes that all clear fluid is being added over the interface, which should not be done, but the reporter believes that the site interface, as seen from here, is thin and unchanging with time. And I agree with the reporter, as the site interface is thin and unchanging with time, you can assume that all the clear fluid is instantaneously added above the suspension layer. Next, there was a discussion on the effect of terminal velocity on the interface velocity, and I agree with the reporter that the enhancement in the interface velocity remains the same, but the actual velocity or the actual interface velocity changes. And lastly, the discussion comes about the PNK theory not being applicable for larger particles. And I agree with the reporter that the enhancement in interface velocity remains the same, and the PNK theory is purely geometric. In summary, the reporter has outlined the significance of convection currents in the phenomenon, which is very important as they directly govern the fluid flow in the phenomenon, but there was no direct answer to the problem statement regarding the parameters affecting the settling rate, including the fluid volume, the base area of the container, and the particle concentration. The opponent has rightly pointed out a lack of investigation into these relevant parameters, but they have missed the lack of discussion into the origin of convection currents, which I feel is very significant as convection directly drives the phenomenon. Thank you.
Okay, thank you. Okay, final concluding remarks from the report. slide with the comparison of the theoretical and experimental results. Okay, I'm wondering why this vertical line starts on a different position here, like experimentally and theoretically. Like why don't these two curves match at the beginning?
Well, I think it was an error because the E0 was actually about 21 centimeters, and 22 was actually the highest point of the liquid, but not of the particles. So this was.
This is the starting point, so like it's shaped, no? Like basically the particles are everywhere. So how is it possible that the theory has a different starting point than your experiment?
So the experiment, I think the experiment doesn't actually have particles there. It's just that I used a bottle and it had this portion there. So that's where the 22 centimeters. The H0 was actually the one where the particles were when the B was still 7 centimeters.
Okay, thank you. Georgi,
size and sorts of particles.
Yes.
And how the theory is to complicate it, so
I believe that the theory will still hold for moderately small particles, but if the particles are very large, on the order of 1 cm, then the convection current wouldn't really be observed, and the convection current wouldn't be large enough to cause the particles to move up the container.
okay, Shafkat? Okay, then Natalie?
Can I ask you if you remember what's your definition of convection in this case?
If I could use the board to draw the convection,
So it is convection of what? Convection of the liquid?
convection of the clear fluid being driven up the container.
Okay.
Yes, my definition of convection is the same. And also,
Right?
so it's not just this part. There's also the suspension layer will be pushed down. So there will also be its velocity will also be downward this way. So the convection occurs in the total volume of the suspension.
Okay, Jacob?
So the theory brought up the volume and the parameters of the liquid and the parameters to vary. What effect do you think this will have?
Sorry, could you repeat
What
that?
effect do you think this will have if you vary the volume of it?
If the volume of the liquid will change, I believe that there will be one main factor that the distance of settling will change. So the particles will move through a greater distance to affect settling time. But another factor that could also change is that, like, for example, if all the fluid is located in this bottom region, then there will be no enhancement to the settling velocity, so the base area is the same.
Okay, so it would change the center of the volume and the height of the initial solution.
Yes.
Okay, I have a question coming back to the rear. So did I get it correct that like your claim is that the main effect here for settling down the sand particles is the convection of the water?
Yes.
So like if we could somehow stop the water and just let the sand move, then we would see something which is significantly different than what we see now.
If the sand moves down, then it will be a simple case of the particles moving vertically downwards.
Okay, but like what we have seen in the experiment would this model with the parameters used by the reporter be significantly different from the reality?
Yeah, it will significantly differ.
Okay. Time for one more last question. If not, I have one. Can I have the slide number 11? Oh, that's here. So what's the precision and accuracy of this number? So did you really measure something on the precision of a micrometer per second or a fraction of a micrometer per second? Really, like you had a way how to measure something on the precision of an 0.0001.
I use this calculation for.
I'm asking about the precision. If you drive your car, you say you drive 100 kilometers per second. You don't say you drive 99.758 kilometers per second. So my question was, to what extent is this number precise? If you say
It is precisely about 3/4 decimals.
Okay.
Okay, grades for the report. Now, 2, 3, 3, 3, and 3. Grades for the opponent. Now, 6, 5, 5, 8, 8. And grades for the reviewer. Now 7, 6, 7, 6, 5. Thank you very much. So the report was graded pretty consistently low. Jacob, you were even a little bit lower than the rest.
Yeah, I mean, I feel like this is referring to as well. I had to one for the report and 0.75 for the discussion, and then about 0.5 for some of the questions that I asked, it's mainly from the opponent on the presentation. I just think that it's fair to use the theory that you used, but what I was really missing was the experimental analysis of the parameters being varied in a different way and comparing to the theory and kind of drawing conclusions from it, because we saw that the set image kind of looks like a theory, but it wasn't to me enough to say that it's accurate, and it wasn't completely easy that way.
Okay, I don't know, Georgi, would you like to briefly comment on 3 on the upward?
For the very high, I would like to give you some suggestions for implementing the presentation covers like the large area of the program, but so what we covered just human presenting and what was not clear, so we were slightly managing just to improve our like views on the report. So it's okay, and quite interesting. So there were a lot of excellent slides, and what we did was not very clear, so try to make the presentation clearer. Just compare the work to start.
Okay, thank you much. Okay. If I think you have seen it become very into the presentation we have seen before today, then there is a big gap, like both in theory and experiment and the presentation part. So like all need to be adjusted. Okay, for the opponent, there were 2 5s. Shashikant, can you comment the 5s?
Yeah, initially I thought we started very good, but later on we just started dragging a particular topic like sedimentation. We spent too much time on discussing just one simple area that she was discussing, and I thought we must have just moved ahead with the other topic. Although I think, though maybe he doesn't have so many points to discuss on it, so I thought if that were be done, so I had given him scores of 1 for asking question, 1.5 for his speech, and 1.5 for discussion with the report.
Okay, thank you very much. And Natalia, your 8 for the opposition.
Yeah, so basically I really like that you brought in the physics of this problem and the physics. So yeah, I always feel like everyone's sitting in the front. I really like that you brought in the physics and that you really tried to, discuss also the main physics, which was not in the presentation, but I think this is important, and this is the main job that you have. And then also you were discussing, also in the presentation, you were also discussing the experiments you did, and what I really like is that you noticed that the rate is not changing much, so the question is whether it was the actual phenomenon which is being observed. I gave you 1.5 questions, 3 for speech, and 3 for discussion. Because I also think it is really
so it was even 8.5.
Yeah. It's really hard to oppose such tasks where there is not that much experimental work done, and I don't really know how much, what's the way to do it much better.
Okay, yeah.
Maybe I say something. We actually kind of agreed that we brought a lot of relevant points in the discussion with the reporter. You just really lost points for me when you started just kind of doing your own presentation now from my number. Oh, sorry. Like I kind of like the content, just on the rating sheet there's also a part about the opponent's conduct at the discussion and just kind of like explaining how the phenomenon works without really discussing with the opponent, especially with the report at the beginning. That's what kind of back.
Okay, and here I have to deeply disagree because this was for me the strongest part of your position, because clearly like the presentation completely lacked the explanation, the simple explanation, and you tried to get it from the reporter, you didn't get it from the reporter, and then you made it by your own. So from my point of view, this was the thing that I would because it's not just your discussion. There's the reviewers, there's the jury, there are other people. So here I have to but that's perfectly fine. That's why we have like 5 or more jurors here. I have to disagree because I believe this was the best you could have been doing, because like sticking on just discussing what was done when it was very little doesn't really bring us further. Okay, you already
Okay. Well, I would say that like George was reviewer and
for reviewer, you're not the lowest, but okay.
Yeah, I agree with my colleagues about that. In the area of the problem is not very too wide. So by the reporter, it is hard to resolve the position, but it is not manageable. It is manageable. It's not the only managing the problems are in this position. I believe that in this case, the balance between two things should be done. One is that you should ask me as the area of the opponent reporter day, so close by, and then you should also give us a clear clarification of what should have done, should have done in the program. It shouldn't be only one, or it should be only two, and it is very sensitive to be near that. So yeah, I think that the very good impression from me was that it was not very good neither from the document or forward reviewer. Well, the points and everything was fine. So I thought it was quite better from the reviewer, so I just gave the reviewer 6 and
okay, so but you gave a 7 for the reviewer.
Yeah. For me, I thought the job of reviewer to review opponent and report, I think he has done justice to it. Obviously, I'm pointing out different points. Obviously, he brought some new point, which I thought was a very important aspect of it. So you have given out, you pointed out a list of points. That's how we
What was the new point?
he was discussing about the volume part of it, volume to the new topic, and he brought it into consideration. And then the base area for the sedimentation, which was a very good point for me over here. So I gave him as a 1.25, 1.25, 1.5, 1, which comes to 7.
Okay, so I gave the lowest grade, sorry for that. Basically, I have to say again, it's mostly based on the physics side, because I here again disagree that the convection is for this area of parameters they have used an important. I'm pretty confident. I would love to discuss it, but I'm pretty confident if it would be possible, say, to freeze the convection somehow, then we would with this large particles and this heavy particles, we would basically see the same, because the PNK theory, it's a geometric theory, the convection is not included in that theory. So I don't agree with you that the convection of the water, the fact that the water flows, makes a significant contribution to the results in that area. It's different for blood cells and really tiny stuff, etc. But here we have seen pretty large sand particles, which basically settle down mostly due to the geometry. The thing is you have geometrically better paths to settle down. So that's why I had to be slightly lower than my colleagues, because here I just scientifically disagree with that point, which you repeatedly mentioned that yes, this was the convection was here. I don't think it was here. I think the PNK theory is not a convection theory. So that's it from my side. Okay, thank you very much for today's physics part. At least I really enjoyed it. It's not always the case. So now please hurry up and take the dinner, because we are behind.